Fine to Scott, and apologies that we got downstairs in the bigger room. It was already pushed.
Thank you so much for being here, especially those standing in the back. It can be a long haul, so I'll try and keep things upbeat and try to help you forget that you're standing for this lecture. So I tried to come up with the most boring title I could, with the hope that I would have a low bar and I could exceed expectations today. So we're going to be talking about groundwater wells, and the dream here is to try and convey what I think is a helpful large data set that is locally relevant, but that we can map the use of groundwater and the hydrogeological conditions at more expansive scales than is common. Okay. Okay, so what does this look like? So I'm from Canada. I'm from Victoria on the west coast there. And the data set I'm going to be talking to you a bit about today is a map of places we've drilled a water well. So this is an excavated structure, drilled, dug, some manner of moving underground for the purpose of extracting water beneath our feet. Groundwater is the world's largest freshwater resource by volume. It's about 99% of all fresh unfrozen water on the planet. That said, it's often a little more slow moving than the lakes and rivers maybe that we're used to. So, but it's a critical resource. It provides a large share of global water use. Before I move too quickly into this, I should mention my collaborator on this is Deborah Perrone, who's also a professor at the University of California in Santa Barbara. Okay, so just to kind of orient you, you're going to see a few maps today of these maps of water wells. And every dot on these maps is an individual decision somebody made to construct a bore for the purpose of extracting water. They do it for different reasons. This is a map of the reason that people have drilled wells across the North American continent. Red being for industrial purposes. You can see the oil and gas rich basins sort of pop out in those bright red colors. Blue for drinking and municipal uses and household uses that we're accustomed to. And then green for agriculture, either support livestock or for irrigation of crops. The second comment I'll just make on that is that we have both a snapshot of why the well was drilled, how deep it is, and then also when it was drilled. So we have some of these records going back to the early 1900s, and it provides what I think is a helpful big data set for not just looking at water use, but also thinking about the history and the land uses throughout the North American continent. Okay, so I like to kind of cut to the chase. So I'm just going to give you my main findings in case you have to leave early. So here they are. Wells are running dry in America, and I would argue this is problematic for, and I think those who had a well run dry would also agree with that. And the second main conclusion is that wells are being drilled deeper than ever before in America, and we're drilling deeper wells far more often than we're drilling shallower wells in America. And I'll suggest to you today that this is an empirical finding, so we're confident in this statement. I'm going to propose to you in a more qualitative sense that this is no more than a stopgap to solve our problems with groundwater overuse in some parts of America. One more comment before I dive into the introduction. I come from the Bren School, and some of my colleagues, dear colleagues of mine, are from fields where it's common to interrupt speakers and chat with them about questions as they arise. So I would just encourage you, if you have a question, feel free to just put your hand up. The more conversational we can make this, highly open to that. So don't feel like you're interrupting. Okay. Great. Okay.
Why are there those states that have nothing?
Yeah, we'll get to that. Yeah, those are so unlike Australia, where where I'll get to my praise for the database you have here. We do things state by state in America. So each individual state has its own, thank you very much, groundwater well completion database. So yeah, we had to go one by one, asking database managers at different state geological surveys, engineering offices, if they would be willing to share their digital database of groundwater completion records. It took us about 4 years to quality control it. The supplement of this paper is longer than my dissertation, so it was quite the job to kind of quality assure these data. So that, yeah, you can already see the ones that on bad behavior in America. So yeah, there you have it. Okay, so 30,000 foot per second here. So of global water use by humanity, these numbers are approximate. They're a little higher in some papers and smaller in others, but about a third of all the water we use as humans derives from groundwater. So it's a non-trivial share of the water we rely on. It's in some places the only perennial supply of drinking climates. Think maybe monsoonal regions where you have times of plenty and times of dry each year when the intertropical root zone sort of sways. And it's often seen as a more resilient resource from a climate variability perspective. You can rely on groundwater to be there next year, but in some ephemeral streams, you can't necessarily predict exactly when there will be flows. What do wells look like? So I sort of emailed my colleagues and asked them if they'd be willing to share a couple pictures of wells. Here's an artesian well. This means that no pump needed, no pump necessary. That you just drill the well down and the water comes flushing up. So it's under pressure at deep depth. Here's another one in Syria, hand pump in Uganda, one in the Philippines, Bangladesh. The wells, we've been at this for a long time. All these wells are going back thousands and thousands of years. So it's been a really critical way to access fresh water for much of our history as humans. Okay, so were you to fly across America and look out your oval window, maybe you'll see it differently after this talk. I hope you might. What I hope you might see as you peer out your window are many lands that are equipped for irrigated agriculture, many rural households that rely on groundwater for their primary source of drinking water. These center pivot systems are in many areas around the world and are indeed a common form of irrigated agriculture. The database on the left is what we've got so far for wells. There's about 12 million of them in America. By no means is that the actual number of wells in the US. We've surveyed each database manager. That's been something that's proved very helpful to us. And asked them the question, okay, of all the wells you have in your database, how many wells do you think you actually have in the state, and what share of those are in your data set? And the answers are highly variable, but sometimes as low as 1 to 5%. So the 12 million number I throw out there, I think I can say with great confidence it's an underestimate of the actual number of wells in the US. Some are never reported for their permit. Report is never reported, or there's just a drilling that is done without permits in the US too. Okay. So we surveyed all of them, and yeah, I guess just as my sort of how we've done science moment, that we've really found it quite helpful to talk to the different database managers. It's been rather remarkable to look at the different variability in the types of data curation across America. In some areas we know our data sets are biased to certain kinds of wells. Some only have recent wells recorded. So there's tremendous variation in the quality of the data sets across the US. So keep that in mind as we march forward here. Okay, so we're doing kind of two different things, and I'm only going to talk about one today. But if you ever invite me back, I'll come do the other one. So we're going to spend time over here. We're using these wells to try and understand how frequently they're running dry. And a dry well, in this case, by us, this isn't the only way a well can run dry, but how we're going to define it is a well at which the water table has dropped at least close to the well bottom, if not below the bottom of the well. So that well is no longer able to extract groundwater. And we're drilling deeper wells, but it won't solve all our problems. Okay, so let's start with part one here. Yeah, what do we know? Well, we know in the US, we know from satellite measurements of gravity, and we know from measurements of individual monitoring wells in America, we know that our groundwater resources are being depleted in a number of areas, especially areas where we rely on groundwater for irrigated agriculture. Some of the more famous aquifers in America, perhaps, are the High Plains in this area. You'll see that outlined in the California Central Valley, are just a couple. So we'll talk about some of these regional aquifers as well. So that's what we know. We know that the groundwater levels are declining. What I would argue we don't have a very good handle on is this. This is a happy well, and it's got its well bottom below something called the water table. So that's just the depth below which all of the cracks and pore spaces in the rocks and sediment are saturated with water. So this is a well that's perfectly able to pump, but if we had some friendly wells alongside, perhaps the water table could decline to such a point that if your well was insufficiently deep, it may not actually be able to tap down to the water table anymore. So simple enough conceptual model, but getting a handle on this is actually tricky and I would argue rarely done. What we do know about wells running dry often derives from the news media. And there's been quite a bit of studies in the US by different reporters of wells running dry. So we know this is happening. We have individual stories of this occurrence. And it can be a real problem for individuals, especially those that can't afford to drill a new deeper well, or if it's not possible to drill a new deeper well in a certain location. This is California, so I live, this is Santa Barbara, so Argunes down here. And this is a particular aquifer that you may have heard of. It's called the California Central Valley. It only covers about 0.5% of America's land mass, so it's relatively small on a map. But it's disproportionately important for food production. So a substantial share of the almonds in America come from this area, and also some of the table food that we rely on. All of the colors here are an individual well in the Central Valley. Most wells are for domestic use. It's a little bit different than actual groundwater use. So that most of our wells, in terms of the number of them, are for household uses in America, but most of the actual pumping is for agriculture in America. So the agricultural wells that do exist pump disproportionate amounts of groundwater, especially compared to domestic wells. There's at least 100,000 in the data set, and their depth is highly variable. We see pockets in red. Red are the deeper wells, and they sort of cluster in some areas, and then blue in other areas where we see shallower wells. So each of these wells represents a decision that someone made, perhaps aided by a drilling company, to decide how deep to penetrate their well. Again, most pumped for irrigation. And what we're sure of in the Central Valley, because we have monitoring wells and satellite measurements and other techniques, is that groundwater levels are in decline. And this led to California passing the Sustainable Groundwater Management Act in 2014 in an effort to try and make things a little more sustainable from a groundwater perspective in California. It's early days, but there's room for optimism here. Wells are running dry. And in California Central Valley, we know this for two reasons, I would argue. One is that the Department of Water Resources allows individuals and county health officials to self-report when a well runs dry. There are some programs to deliver aid for individuals. That said, there's reason to suspect that maybe some county health officials or individuals are more likely to report than others. So it's hard to say that this is actually a representative sample of the spatial distribution of these dry wells. So what we tried to do is actually try and do this with some actual hydrogeological measurements to get a sense of where the water table is at today. So that's how deep you would have to dig a hole in the Central Valley until it started filling in with water. And once we know that, we can then compare that to the depth of bores to try and get a sense of which ones might be dry. So that's the goal. Try and get a sense of this water table. We know the well depths. That's easy enough to take the state databases of these well completion reports have provided that to us. The water table is a little trickier, and so bear with me. If you're going to turn on your mathematical hat, this is the good time to do it. Were you to look at a board, there's monitoring wells around here. I went and visited a couple on Monday through the wonderful app that you have with find wells very easily in Australia. Were you to peer down one of these wells, you would, at some point, as long as it wasn't a dry well, reach water. And those measurements are made routinely across America. So they're the depth from the land surface down to water in a well. So we have lots of those, and that's wonderful. But what we really want is this estimate of the water table. So that's the depth from the land surface down to the depth at which all pores below are saturated with water. What I'm going to posit to you is that the level of well waters doesn't necessarily give us the level of the water table. And here's why. If there's a flow gradient in a groundwater system, so if the groundwater is flowing upwards or downwards through porous media, that implies that there's also a gradient in the hydraulic head. So it means that a measurement made at a shallower depth may give you a different well water level than a measurement made at a deeper well. So here's an example of a shallow well, measuring you think of it kind of like pressure, but hydraulic head is a better term, measuring that hydraulic head at that location. And here's a deeper well measuring a different hydraulic head in this location. Because the deeper well has a deeper water level, this implies that there's a gradient from shallower elevations down to deeper elevations in terms of the flow potential in this groundwater system. So this is a bit pesky for us, right? What we'd really like to be able to do is take these well water level measurements, and if they were all the water table, we'd be done. We'd have that, and we could figure out which wells have run dry. But we don't, so we have to do a little more than that. And this isn't just a one-off. When we look at well water levels and well depths, consistently we find that the shallow wells, so shallow down here, tend to have shallower water levels. And in a similar location, a 1 square kilometer, 1 square mile area, a deeper well will have a deeper water level. And And we find this in California, we find this in Montana, we find this in Minnesota. All the yellow dots are wells, by the way, and this is a satellite image. It gives you a sense of the density of this data set. And we find it in Louisiana. We find it, in fact, all across America. When we plot a rank correlation, so we use a rank because it's a little better, it's a little less susceptible to outliers and sort of values that you don't necessarily want steering your regression the way Pearson regression would be steered. When we do a Spearman rank regression of the well water level elevation versus the well bottom, so think of it well depths and well water levels, we see that almost all of America is red. And in this case, red implies a downward vertical hydraulic gradient exists. Said another way, if you were to put yourself in America for a moment, and you were to drill 2 wells right here, one shallow, one deep, in most of America, the water level in the well, in the deep well, will be deeper than that in the shallow well. Give me a quick nod if this made some sense. I'm giving kind of 30% up.
That's if you don't have any artesian base, isn't it?
So that's a very good question. Yeah, so the artesian ones, just like that Wyoming well, there are some, and many of them have been underwater, so they maybe were artesian and are no longer. But you're right, some are. And in those cases, you can have it can really be the other way around. Exactly, you know this very well. But the deep wells can just come right to the surface and you'll see it the other way. But it looks like, at least this is 2000 onwards, these data here, looks like that's not the norm. We see it in a couple of spots, and maybe in particular this is the Platte River. So that's maybe an area where groundwater is discharging and generating stream flow, but it doesn't appear to be the norm. Yeah.
You might be missing something, but you check this with nested wells.
Yeah, that's a
Maybe
really,
I'm misunderstanding
that's a
how
really
you
good way to
get
think of it.
this
I don't want to. I think if I said nested wells, I'd be being too kind to it because we're using constructed well water level measurements. But that's a really good way to think of it, and that we're doing wells in a similar 1 square mile area and comparing the regressions of water levels and well bottoms.
Okay.
So it's kind of like a nested well, and we use elevations rather than depth, so that if there's land surface variability, on the channel, get at that. Yeah, that's a really good question. Okay, so you'll see a little bit more of it for those that didn't nod as strongly as others here. So here's a location in California, sort of a hypothetical one. What we'd really like to do is for every single well, where people are actually using these wells for either food production or for their drinking supply, so I would argue they're important, at least to somebody. What we'd really like to know is, are these wells still below the water table or not? So we need to calculate this water table. And others have kind of put together some pieces of this too. One approach that we're thinking might be suitable, building on works of others, is that if we can collect a large number of well water level measurements in one location, so within a radius of that well, we can vary that radius with a sensitivity analysis. So wells within a similar location with water levels, we often find, just like we've shown before, that the deeper wells tend to have deeper water levels. What we're really after here, though, if you kind of put your maybe kind of Einstein thought experiment hat on for a second here, you really want the well that doesn't exist. You want to know the well that is just deep enough to touch the surface of that water table. That's kind of what we're after, right? Said another way, it's the well where this distance from the bottom of the well to the top of the water level is infinitesimally small, very small, microscopic fraction, wedge of water at the bottom of the well. We never have those, rarely have those, because who would ever drill just to where the water, usually we drill a little deeper than the water table. So we have to go into kind of regression space, and necessarily we are always out of sample with these regressions, so I acknowledge this fully, but it's the best we've been able to come up with from an empirical perspective to get at this. There's a lot of words here, but just think of that as this vertical distance here, okay? So it's this wedge, and really what we're after is when that's 0. Because when that's 0, that's that hypothetical well that we don't have, that doesn't exist, where the water level is just at the bottom, and that gives us our depth of the water table. So we can take this kind of wedge of water here and find the point at which that hits 0 and the well bottom elevation that would hypothetically give us that elevation. That's how we've tried to get at this. It's not to say it's the only way. In fact, there's certainly going to be some other ways to get at this, but it's one of the only ways we could think of doing this with purely empirical data. So that's where we're at now. Okay, so you've heard enough about the methods. Let's jump to some conclusions. So if you buy that all these well water level measurements that we have in different wells of different depths can be coalesce and are kind of stronger together than they are on their own, because they can give us a water table elevation rather than just a well water level elevation. So if you buy that through these methods, you can then get a sense of the depth to the water table throughout California's Central Valley. And it's quite deep in some areas and shallower in others. this is all we need. We've got the water table depth. We know our well depths. So here's our well water level measurements. Here's that regression space that I'm proposing we might be able to use. Here's our water table depth. Here's our well depth. So all we need to do is compare the depth of the well and the depth of the water table, and just ask the question, is the bottom of the well still wet or not? And the answer is, for most wells, yes. Yeah.
Sorry.
Yeah.
What's the difference between the well water and the water table depth?
Yeah,
Was it worthwhile?
it's a really good question,
Or
yeah.
that?
Probably a better way to do this is to show you this. Yeah, this will be suitable, I suppose. So, you know it'll be, given that there's a downward hydraulic gradient, you know the calculated water table will be shallower than, almost always will be shallower than the shallowest measured well water level. So think the water table in this space would end up somewhere in here, but in this case 20 meters, but in other areas perhaps much more. So yeah, maybe here's a suitable example. So we know the shallow wells in this location have water levels only a couple meters below the surface, but here's a well that is down at about 110 meters and its water level is 90 meters, so it can be considerable. One of the ramifications of this, and I guess I have to say this kind of softly while I see the camera phones in the back, but I don't know if we've ever really made a good measurement of the water table, or if we have, we've done it maybe less frequently than we think we have as hydrologists.
There's a lot of pumping around.
Yeah, yeah,
And so it's done with this
yeah.
drawdown cones and things like that.
Yeah, I was hoping you'd say that. Yeah, so the measurements themselves are static water level measurements made by drillers. The second part might raise some eyebrows. So what we did is we compared monitoring wells at a similar location to a constructed well, and when they have similar depths, so we did around this thing. And just said, are we getting a similar answer from our constructed well, which has a water level measurement made by a driller, as we are at the monitoring well? And the answer is yes. So the upshot of that might be, my answer to your question is yes. Real pumping is happening even when we make these measurements. And especially in California, it doesn't really stop. So it's kind of part of the system at this stage. And I think my hunch is that I don't have any data to back this up. I have a hunch that's maybe why we see these downward hydraulic gradients. They might not all be natural. Okay. Okay, so let's go to some conclusions here. So this is the self-reported examples of wells that have run dry in California Central Valley. And here's the water table elevation minus the well bottom elevation. So don't get too distracted by the words. Anything in red means a well is in trouble. Anything in blue means that there's at least 20 meters between bottom of the well and top of the water table that we've estimated. So the upshot is that we're looking at about 1 in 20 wells in the Central Valley. That's maybe a bit of a generous statement. It doesn't sound quite as dire as it is, because there are some areas that are where these dry wells are quite heavily clustered. They're densely distributed. So the next question might be is which individuals are being impacted most by wells running dry? We've got some individuals that are using wells for household uses, some that are using wells for irrigated agriculture. The individual with the deepest straw tends to be a little more resilient to a declining water table, purely in the context of the well running dry. So let's see who has the deepest straws. Okay, and the winner in California for deepest straw is often agricultural wells. This is the same sort of water table elevation minus well bottom elevation. So just think of it as these are statistical distributions, and any wells that are in the kind of colors here are in the danger zone where they might be running dry. So the upshot is that domestic wells are disproportionately vulnerable to running dry because they are shallower than agricultural wells in the California Central Valley. Most of the pumping in California Central Valley is coming from agricultural wells. So I guess I'll leave that there as things I know to be true, and say that you can fill in the gaps as to maybe some of the kind of environmental justice aspects of this in California Central Valley as well. And this is for the entire Central Valley, but if we look at it spatially, anything in green means the median agricultural well is deeper than the median domestic well. It's the norm almost everywhere. Median ag wells are deeper than median domestic wells. So this is kind of our conceptual model. When wells run dry, they're often for individuals that are keen on using that water from their homes, whereas agricultural wells are known to extract a proportionally higher amount of water per year compared to domestic wells. Okay. One other kind of interesting correlation that's popped out from this. This is a tough plot to kind of wrap your head around, but it's a comparison of the difference in well depths between agricultural and domestic. So anything up here means that the typical agricultural well is deeper than the typical domestic well, if you're up above this line. And down here, this looks at groundwater withdrawals at a county scale. So anything to the right of the line here means agriculture is using more groundwater than domestic wells in that county. Almost everywhere in California, plots up here. In fact, it's almost, you can almost squint and sort of see a log relationship here. I wasn't brave enough to put a correlation coefficient up here, but it's, you can see that there are some areas where agricultural water use is about 100 times higher. Groundwater use is about 100 times higher than domestic water use. And that said, the typical agricultural well is about twice as deep as a typical domestic well in these areas. Okay, so that's it. Groundwater levels are declining. About 1 in 20 wells have run dry. Domestic wells are disproportionately vulnerable. That kind of wraps up the first part of the talk. Before I dive into the second part, does anyone want to share a comment or a question on this part? Yeah. My best answer is I don't know. And read into that how you will. As someone, I'm trained as a hydrologist, not necessarily an water lawyer. I think I'll be brave enough to say that if they do exist, they're probably not going far enough at this stage. There are some grant programs and yeah, ways to work with individuals who have had a well run dry to help supply water to them, often by trucking water in, using these kind of stopgap solutions. But at least in the data, it appears that if those policies do exist, they haven't solved the disconnect.
Central Valley's had huge consolidation, isn't it?
Yeah.
Similar
Great
to what
question.
this is based on elevation, surface elevation. I'm just wondering how that
That's a really thoughtful question. So
messes with things.
Yeah, that's a really expert question. So Central Valley has been dewatering the clay layers, which are responsible for a lot of great deal of collapse. And so the land has sunk substantially. There's a rather famous picture of a hydrologist standing next to a telephone pole, and that telephone pole represents about where the land surface was in sort of 50 years prior. So there's been a substantial amount of compaction here. The water table analysis we ran was purely in a slice of time, in a recent slice of time. So, but you were right, were we to try and do a time series of the water table, I'd actually have to kind of think about how you want to do that. You want almost the elevation of the water table minus the elevation of the land surface, but also include that time varying elevation of land surface. And I don't think those data exist, so that's a really thoughtful question. Okay, so wells are running dry. I hope I may have convinced some of you by that, but so what are we doing about it? Well, were your well to run dry, something you might consider doing were you to have the capital and nearby drill rig or friend of one, is to consider drilling a deeper well, especially if you're reliant on that for your supply of water. So let's go to this great big sort of continental scale, or continent-wide anyway, scale. So these are the reasons we've drilled wells in America. Green agriculture, blue domestic, red industry. Some biases state by state that kind of pop out here. So things like this green-blue divide is somewhat artificial due to record-keeping issues, but it somewhat gives you a sense of what we've been up to across America. You can start to see even bends like the Mississippi River in here, the embayment. I see things like the High Plains Aquifer, the Denver Basin. So this map of purposes give you a sense of why we drilled for water. So here's another map. This is a map of the depth we drilled for water. And again, you're starting to see things like water demand. Where do we want groundwater? So groundwater wells are drilled in places where we'd like to use groundwater. So that's one aspect you might see in this map. You might start to see policy, some of you that are trained in that aspect. You can even start to see rivers and accumulating depth of wells alone. So this data set is, I've spent many an hour just sort of staring at it. And I think there's quite a bit in here, and things that my eye, trained as a hydrogeologist, sees, and also things that my eye, trained as a hydrogeologist, does not see probably as well as many human beings. So it's been a fun data set to work with. But so what have we done with it? So one thing we've done, going back to this drilling deeper aspect, is we've taken a look at, through time, how deep is a typical well in a given location. Kind of take a snapshot of area, and just ask the question, are we drilling deeper over time or not? Here's one example where the answer is yes, absolutely, from 1950 to present. I'm not going to speculate today too much on the reasons why this is happening. That will be spatially variable, and there will be many of them. happy to talk about some that I've read about, but what we can say with confidence is that it's certainly happening in Stockton, California. Let's see if it's happening elsewhere. So what we've done, we've kind of come at this a couple different ways to just do our best to make sure that we're somewhat immune to sampling biases. So all these little polygons are this kind of cool tool in ArcGIS Pro that zips around and makes polygons that have roughly an equal number of points in them. So we kind of did that to make polygons with about 100 points in them, spanning, in this case, the years 1950 to 1975. And then we took a look at the regression between time and well depth. And again, we use the Spearman-Rank correlation coefficient just because their geology is complicated, especially when you look at these expansive spatial scales. So Pearson regressions are not necessarily something to write home about, but Spearman-Ranks gives a sense of just if we're going up or down. It says nothing about how fast we're going up or down. Anything in blue means we are drilling shallower over time. So my grandfather's well was deeper than my well that I'm drilling tomorrow. Anything in red implies that the wells farther back in time, constructed back then, tended to be a little bit shallower than those constructed in the future. We've done this sort of for different time intervals. The upshot conclusion is that we're drilling deeper a lot more often than we're drilling shallower. So if you look at the Spearman-Rank correlation coefficient, 3/4 or so for this time interval are in the red zone. If we exclude all the polygons that don't meet a p-value of 0.05, so we're looking at the ones that maybe have a little more statistical confidence, that conclusion becomes, if anything, strong. We can do that from 1950 to 1975. We can do that from 1950 to 1975. We can also do that at different time intervals too. So there's 1975 to 2000. Again, far more frequently we see drilling deeper rather than drilling shallower over time. We can do that for more recent years, 2000 to 2015, same conclusions. We can then sort of broaden our gaze and take a look at 1975 to 2015. You're seeing a pattern here. There's a lot of red on this map, and it doesn't go away. We've tried things, and it's just it's pretty robust. So maybe this doesn't surprise you. You know, technology's improved since 1950. Pump technology's improved since 1950. There are a multitude of reasons why we might be drilling deeper. I guess my conclusion today is that we are in America. I tried to be a good speaker today, and also I've had some sleepless nights. Just jet lag is kicking in. So anyway, there's a really remarkable database here at BOM. Best in the Commonwealth, spoken as a Canadian. So you've done things so well. You've got it under one umbrella. America, it took us 4 years to chase all these data sets around from these different database managers, and you know, it's kind of like painting the Golden Gate Bridge. Now that we're done, we almost have to start again because the first data we compiled is almost outdated. So anyway, you've got it good here, better than you know, perhaps. And I had fun with my app in this database running around New York City trying to find wells on Monday. There's a beautiful one in it's a Royal Park with the circular track in the north there. I must have got that wrong. Oh, it's a couple months in there. Well, anyway, there's a beautiful monitoring out there. So anyway, are we drilling deeper in Australia? And the answer is yes. We did this in sort of 10-kilometer squares. This is quickly done compared to the polygons on ArcGIS Pro on my laptop. But the upshot in Australia is that where we have some confidence in running these analyses, we have at least 10 points in this 10-kilometer square, and at least 1 point in the first 5 years and 1 point in the last 5 years, so have some continuity among those years. This is for 1975 to 2015, and the conclusion is that you're also drilling deeper in Australia. It's about 80% of these squares are at least higher than 0, and there's more dark red than dark blue by a long shot, meaning that the places where we have a strong correlation coefficient are almost much disproportionately often are drilling deeper trends. Okay, so shallow wells are running dry. Wells are being drilled deeper, and I guess the conversation I'd really appreciate having the chance to start with you is that I would posit that drilling deeper is an unsustainable stopgap to groundwater depletion. And there's a few reasons why I proposed this to you, but before we do that, let me show you a little more data. So here's an analysis we're going to do. We're going to look at all sorts of monitoring wells. A monitoring well is a well that was constructed, and then we've measured the water level in that well over time. And what we'd like to test is to ask the question, are we drilling deeper in places where water levels are declining over time? So the way we do this is find places with a monitoring well, and we look at constructed wells, the black wells here, within a sort of a small radius of maybe 2 kilometers for this case, or 5 kilometers of that distance across America to try and compare trends in groundwater levels and trends in drilling over the same time interval. So to kind of get you accustomed to, these are interesting plots. Here's a couple of examples. Stockton, California, here's the water level in blue, and the yellow octagons are any occurrence where someone has drilled a well through time. So you'll see that we're drilling deeper. The yellow wells tend to be deeper over time, from 1950 to 2015, and if you squint maybe, but the water level is also dropping. So the water level time series, we've seen about 19 meters of decline in the water level, about 3 meters a decade. Here's the wells. We're seeing about 7 meters a decade. So in California Central Valley, we tend to find that not only are our groundwater levels declining in the majority of our monitoring wells, but nearby those declining groundwater levels, measured at monitoring wells, we're also finding that individuals have drilled deeper over time at a rate that outpaces the decline in water level of that well. Could be some risk aversion at play. I don't know the social science behind this, but the empirical conclusion is pretty strong. That we're drilling deeper about twice as fast as the water levels are declining in California Central Valley. And we can do this in some aquifers, particularly those that have nice, thick alluvial sediments that are permeable and extend to great depths. That's not necessarily the case everywhere. So yeah, the upshot is that how are groundwater users reacting? They possibly are drilling deeper in places where groundwater levels are declining. But here's another example. It's on the fringes of something called the High Plains Aquifer, right on the southwest tip here. Looking at effectively the same thing. Water level near Portales, New Mexico, and then nearby constructed water wells. Almost the exact same trend in the groundwater level. So we've seen about the same amount of depletion over that time interval, 3 meters a decade. But we're not drilling deeper that much. And you can pick this apart, but I bet if you pulled out some of these real early wells, that might look like a pretty flat line. So what am I suggesting here? I'm suggesting that in Portales, New Mexico, they've potentially hit some sort of bottom of this aquifer, or at least the bottom of the depth at which it's useful to drill a well. This is probably lithologically confined in this area. We've dove into some consultants' reports, and these local consultant reports say that deep groundwater is of low quality and also of low quantity, implying the wells that are drilled below the High Plains Aquifer can't pump the water. Okay, so those are just 2 examples. Let's try and do this everywhere. We've got these monitoring wells all over the place in America. Let's take a look and just see at these 17,000 monitoring wells across America. Are there some patterns in places where we're finding drilling deeper and declining water levels? Or are there places like New Mexico where water levels are declining and it's possible that we can't drill deeper anymore? And so there is some inevitable day zero or days zero ahead where we might have to think about a different water supply in these areas. Okay, so the plots I'm going to show are correlation coefficients of water levels and well depths. A little bit to think about here, but think of it this way. Anything in the top half of the plot is an increasing water level. Any points the plot down here are decreasing. And these points represent the monitoring well, this is for the increasing and decreasing water levels, and then the surrounding constructed wells and the trends in their depths. If the wells have been constructed deeper over time, we'll be to the right of this line. If they've been constructed shallower over time, we'll be to the left. So just to give you a sense of where things might plot here, the Stockton, California case that we just learned about, we're drilling deeper and the water level's declining. So that would put us in this lower right quadrant. Okay? Well depth trend is positive, so higher numbers over time, deeper depths over time. And the water level in this case is declining. In this case, it's measured water level from land surface, so it's a negative value. Okay, so the upshot is, you saw this at one monitoring well in California, but it kind of pops out everywhere. In California, Central Valley, we tend to find that the great majority of these comparisons of monitoring wells and constructed wells show a trend that's consistent with both declining water levels in the well over time and also deeper drilling over time. Okay, New Mexico, remember this one? This is still declining water level, so we're down below this line here. But in this case, our correlation coefficient for yeah, looking at how well completion depths have varied over time is pretty weak. Consistent with, perhaps, not much of a trend towards deeper depths. So we find this everywhere in the region here. In fact, there's some areas where, for some reason, we see really strong trends in the water level declining and shallower drilling over time. So it's possible that there are some areas where we're kind of stuck, and the wells we have today are about as deep as we can go to be helpful to us. We did this in an effort to kind of juxtapose the different aquifers across America. We long mapped these aquifers and mapped the depletion rates of water levels in the monitoring wells, but what we're hoping to do is kind of take maybe a different lens at this and have a look at how individuals have made decisions captured through the completion of well and the well construction records to see how they've responded to areas where well water levels decline. And the kind of upshot of this is that California's Central Valley, in red here, looks very different than the Central High Plains and the Southern High Plains. All of these locations, Central, Southern High Plains, here, here, and California Central Valley, we often see declining water levels in the wells. But in California, those declining water levels are being met with deeper drilling. And in the High Plains, that is not true as frequently. So wells are not being constructed deeper in all of the areas where groundwater levels are dropping. There is some data on 3D geological information across America. This is a map to sort of the depth to what has been used and referred to as the bottom of the aquifer for the High Plains. Some wells below that can still be useful, but you can kind of think of it like this. What's the difference between the bottom of an existing well and the top of the bottom, that's the bottom of the aquifer? And if that's small, it's possible that we can't necessarily drill that much deeper. When we compare the depth of wells to the depth to this low permeability bedrock, so it's this value, we tend to see a lot of red, implying the well bottom is less than 20 meters from the base of the aquifer. So it's possible that in the High Plains we don't necessarily have the option to drill deeper wells in all locations. Okay, great. Okay, well let me finish up with this then. I would propose that there's a few limits to deeper drilling. One would be hydrogeologic, that's what we just chatted about. So in some locations, yeah, sure you can put a well down there, but it just might not yield that much groundwater. And so it might be sort of a plausibility or usefulness limit to the depth we can drill wells. There's also groundwater quality limitations. In some areas in America, salinity increases with depth, often abruptly and in strange ways, because it's a heterogeneous world beneath our feet. Australia sometimes that's kind of flipped on its head, but we don't see the same water, shallower depths. But I guess what I would also posit is that groundwater quality can also pose a limitation to the depth at which we can construct wells. Particularly in coastal areas, this is Florida, there are areas now where the well bottom is less than 50 meters above the estimate to the depth of saline water. That's in this case treated from seawater and treated into the aquifer. So there are areas where we can't necessarily drill deeper and expect to still have fresh water in our well. This one is, maybe I'm just sort of highlighting my own interest here, but just from a sort of what are we made of perspective. We're all made of water, but how old is that water? There are some areas in America where some of us are now made up of ancient water. You head into the Great Artesian Basin, and some of those wells that are down several hundred meters, the water is ancient there, sometimes millions of years old. So the same sort of thing in America. You tend to find that, once you get down past kind of 200 to 400 meters, very spatially immensely, but that's sort of the order of magnitude scale. Some of those wells are pumping water that was replenished when my country, Canada, was covered by a giant ice sheet. The climate looked very different than it does today. So there's some questions of sustainability and renewal that maybe arise. And last but not least, and this is the one where I value the opinions of those in the room because this is not my training, but I do appreciate that this limitation likely exists in some places. It's possible that there are socioeconomic limitations for individuals to construct deeper wells. Drilling wells can be really expensive. We hired an individual to help us compile estimates from media reports as to how much it costs to drill a well in California. And the upshot is that a domestic well is kind of tens of thousands of dollars in the Central Valley. An agricultural well is hundreds of thousands of dollars, and a municipal well is about $1 million. So there are some non-trivial finances here when it comes to constructing these wells. There's also an issue that, if you remember back to this map, the red one, those deeper wells are frequently going to have deeper well water levels, so they also require more energy intensity to lift that water up to the land surface. And if that lift is powered by carbon-intensive fuels, it's possible that we're also increasing the energy intensity and carbon intensity of groundwater pumping in America as we drill deeper. Okay, so this kind of sums it up. This is from one of those media reports. People don't have the money to drill new wells, and that's the biggest problem. Main findings: wells are going dry. Water wells are being drilled deeper than ever, and I would posit that this strategy is little more than a stopgap in some parts of America. I really hope I have a few moments for questions. Thanks so much for coming today.